stop. Have you ever wondered about the mechanics behind sports such as football and basketball? Have you ever wondered about the dodges, the hurdles, the big plays? Well, in today's episode of Physics Live, we're going to dive into this and more. We're going to look at kinematics and momentum, the cornerstone of physics and sports.
Hear Physics Live. Physics Live.
Physics Live!
Physics Live.
Physics Live!
Physics Live. What is kinematics?
What is kinematics?
What is kinematics?
So you want to know what kinematics is? Kinematics is what we use to describe motion, to predict what we don't know and label it. Kinematics has three components: position, velocity, and acceleration. Position is how far you are from a decided origin. For example, this cone. Right now, I'm at 0 because I'm right at the cone. But as I move away from the cone, my position increases. Velocity is simple enough. It's just how fast you're moving away from the cone. So if I walk away, I'm not moving with a speed, which means that my velocity has increased. Acceleration is how fast your velocity is changing. So if I go from a walk to a run, you can say my acceleration increased. All of these are mathematically related, but for the purposes of our show, all you need to know is that that's what we're going to be using to describe motion. Kinematics lets me do stuff like this. Thanks, kinematics.
Now, look at this car. When the car is at t equals 0, as you can see on the stopwatch, the position, velocity, and acceleration are all 0. Look what happens when we press on the gas.
Go.
Now, when the car takes off, it takes off with a non-zero acceleration, thus allowing it to move away from the origin, the cone, and move on to its final destination. From there, we're able to figure out, using kinematics equations, what the missing components are if we do not record them all, and all the other data from that.
In this case, the missing component was acceleration. First things first, we need to mark down everything we do know. We know that when the time was 0, the car was at rest, so velocity initial is equal to 0. And we also know that the car traveled 19.81 meters in 3.22 seconds, and that its final velocity was 5.91 meters, based on the speedometer in the car. So now we just pull up one of our kinematics equations. You don't need to memorize these. Now, you'll see that A is in the equation, and based on algebra, we can manipulate this equation in order to isolate, and that looks like this. Now, we just plug in the variables in their place, and that looks like this. So after that, we can just put everything into a calculator, and we get that acceleration is equal to 1.84 meters per second squared.
Now, with kinematics, we're able to figure out any unknown component of motion, whether it be in a car like earlier or football. Now we're going to see a throw from a co-host, and we're going to see any unknown component of motion.
Right now, Tamari's about 10 meters away. You have the stopwatch ready?
Yes. Now, we can see on the stopwatch here, 1.34 seconds. And from there, since we also know the distance of 10 meters, we're able to figure out velocity and acceleration.
Just like with the car, we can use kinematics to find any unknown components of motion, which in this case is velocity. As noted, we were 10 meters apart when we started, and the ball traveled in 1.34 seconds. This one is as easy as velocity equals distance over time, and we can just put that into a calculator. So that means that the velocity must have been equal to around 7.46 meters per second.
Unfortunately, this kind of kinematics has a flaw. It only works in 1D, meaning it only works if the object is moving back and forth. In the real world, it is very rarely the case that an object is moving in a straight line. Quarterbacks simply don't have the arm strength to zip a bullet 50 yards down the field, and you certainly can't make a basket by hurling at the backboard. Instead, in the real world, what we find is that balls often move in a parabola, like so.
In order to accurately describe parabolic motion, we must use trigonometry. First, we split the motion of the ball into two axes, the y-axis the x-axis. Then, let's say we launch a ball at 15 meters per second at an angle of 45 degrees. We use trigonometry to find that the y-axis is at 15 sine of 45 meters per second and the x-axis at 15 cosine of 45 meters per second. Two important things to note. One is that on the x-axis, velocity is constant. That means the velocity does not change at all. But on the y-axis, it accelerates downward. That's because of gravity. Gravity on Earth is 9.8 meters per second.
Any questions, class?
Oh, yeah. Are we gonna have homework on this?
Introducing the Torquenator. If dog is man's best friend, the Torquenator is dog's best friend. The Torquenator takes advantage of a simple physics trick, torque. Since torque is equal to force times distance from the center, the Torquenator cranks up the distance, allowing for the torque of the ball to be 10 times what your arm could ever do. Just look at the speed of it. But unlike regular ball launchers that crumple under normal torque conditions, the Torquenator is made out of aerospace-grade aluminum, allowing it to be used 24/7. If you think your dog is energetic, just wait till he meets the Torquenator. Guaranteed to put him right to sleep. The Torquenator, dog's best friend. May cause death or paralysis.
Physics Live.
Physics Live.
Physics Live.
What is momentum?
What is momentum?
You might be familiar with Newton's first law of motion, the law of inertia. The law states that an object at rest stays at rest, and an object in motion stays in motion. Momentum specifically refers to the second half of that statement, which in momentum measures how much an object wants to continue in motion. Now, momentum and its equation is made up of mass and velocity, so increasing either of them increases the total momentum. Now we're going to have a live demonstration of momentum. We're going to see two people of varied masses ride this bike and attempt to stop. Now let's meet our contestants.
I'm Jordan, I'm 120 pounds, 54 kilograms. I'm just here.
My name is Adidas. I'm 196 pounds, 89 kilos, and I'm here to win.
Now let's have one of the participants, Jordan, explain the results.
As the results shown, I stopped before Adidas did. That is because of my smaller mass making my momentum less than his.
Another important concept to cover is impulse. Impulse is caused by external forces acting upon an object. These external forces cause a change in momentum. Impulse is critical for allowing sports such as tennis and baseball to be played properly.
In these sports, the aim of the game is to hit the ball with another object. Impulse comes into play when the two objects come into contact, each at a different velocity. The momentum of the racket or bat is transferred into the ball, causing a change in momentum in each of the objects, creating an impulse and sending the ball hurling at incredible speeds. But at the moment contact is made, another special thing is happening: collisions.
In order to understand collisions, you need to understand the conservation of momentum. No matter what happens during a collision, physics states that the total momentum of a system will not change from start to finish. However, there are two classifications of collisions. The first being inelastic. In an inelastic collision, the two objects will stick together, creating a slower speed with the new combined mass. A common example of inelastic collisions is the tackle.
The tackle, while extremely simple, is a perfect example of an inelastic collision. Two objects combined with one increased mass and lowered speed. Let's slow it down. Right now, two objects, the players, are moving towards one another with their respective masses and velocities. But as they inelastically collide, the tackler takes the carrier off the ground, essentially adding the carrier's weight to his own. You can also clearly see the tackler slows down significantly after picking up the carrier. This is because of the conservation of momentum. The total system momentum before the tackle and after are equal, and since the masses combined, the velocity must decrease to satisfy the rule.
The second kind of collisions is elastic collisions. In this type of collision, the two objects bounce off each other instead of absorbing each other's energy. Here's an example of such a collision. As you can see, the two balls hit and then they bounce away. Just like in elastic collisions, momentum is conserved, but unlike in elastic collisions, kinetic energy is also conserved.
Just like the previous kind of collision, elastic collisions still follow the law of conservation of momentum. Just now, the two objects are not combining and therefore are not required to have the same velocity. Instead, using the fact that kinetic energy is conserved, you can use energy to find the velocities. But we will not cover that today. In fact, that is all we have time for today. Thanks for stopping by.
Physics Live.
Physics Live.
Physics Live! Physics Live! Yeah! Physics Live!